So welcome to Mathematics for Machine Learning Part 3. This will be about distance functions. Most people think they know how to measure distance, and you're probably right under certain circumstances. And all we're going to do today is broaden that idea for you. A distance function is a function with two inputs and where the output is a real number. By a real number, I mean any number that can be represented as a decimal. One thing you'll notice there is that the two inputs could be anything at all. I just say it's two inputs. They should come from the same collection, whatever that collection is, but that's it. We're going to have the following properties. So if I have any three inputs, we'll call them x, y, and z. The question is, what should we expect from a function that's going to measure distance? The first one is distance between 2 points should always be greater than or equal to 0, and the distance should only be 0 when the 2 points are the same, or the two inputs are the same. And so any two inputs that are not the same should have some distance between them. The second condition is also pretty obvious. If you measure the distance from x to y, you should get the same as if you measured the distance from y to x. Whatever your inputs are, if you reverse direction, that shouldn't change the measurement of the distance. And the last one is probably the least sort of obvious, but when you think about it the right way, it also makes a whole lot of sense. The last one is that if you go from x to z through an intermediate point y, that should be just as far or farther than if you went straight from x to z. And so it's sort of the shortest distance between 2 points is a straight line idea. In mathematics, we typically call that the triangle inequality. So the first one's called the function is what's called positive definite, always not negative, and it's only 0 when the 2 points are equal is the idea of positive definite. The second one is called symmetry, and the third one is called the triangle inequality. So those are the three characteristics of any distance function in any circumstances. And so that's the general, very general idea of what a distance function is. And so we'll take a look at some examples that are familiar and some examples that are less familiar. First example is going to be probably the most familiar, which is the L2 or Pythagorean metric. So here, I'm going to let x be a point in the xy plane, let y be a point in the xy plane. Then the distance between x, y points is, well, you take the difference in the x coordinates and square that, take the difference in the y coordinates, square that, take the square root of the whole 9 yards. And we call it Pythagorean distance because that's just the Pythagorean formula for finding the hypotenuse of a right triangle. So the x coordinates, the difference in the x coordinates makes one leg, the difference in the y coordinates makes a second leg, and then the hypotenuse squared is the sum of those two squares. In fancy mathematics, we call that L2, and it's the 2 relates to the square and the square root, the exponents there. So this is the traditional thing in high school algebra and calculus. That's the distance between 2 points in the xy plane typically. So you can also, if you have many more dimensions than that, then you can certainly expand that. And so if I have distance x, y in a high dimensional space, you're just going to go ahead and add on all the other coordinates, and there's no problem with that in order to get a Pythagorean L2 metric distance function in however many dimensions. And you'll notice I'll give up there because I've run out of letters of the alphabet, and that's why in higher dimensions we typically don't use letters of the alphabet in sequence to give the coordinates, and that's fine. We won't worry about that too much. Another common metric is a taxi cab metric, or the L1 metric. In this case, if same x and y, distance from x to y is, we're just going to take absolute value instead and add those up. And so the absolute value is going to force us to be positive. It helps us with that positive definite piece. And then you just add up all the absolute values of the differences. That's a L1 metric. So you'll see that as an option in some of the scikit-learn functions as a way to measure distance between points. And there are reasons to use that sometimes. And then LP in general, we're just going to use the power P here, and there's no magic to P, it's just tradition why we use the letter P there. You apply the power P on the inside to absolute value of differences, and then you apply the 1 over P, the Pth root on the outside. And so L1 is an example of that. You've got a first power on the absolute value, you've got a first root, which is, doesn't change anything on the outside. On the L2, you've got a square and a square root. You can do an L3 metric where you cube and then take the cube root. And anytime that P is an odd integer or not an integer at all, you have to have the absolute value so that you have a positive number when you're taking the Pth root. And you have to have the absolute value in order to have positive definite as well. So it avoids the problem with negative roots, it avoids the problem of negative numbers where you're trying to take fractional powers, it avoids the problem of losing positive definite. So we need those absolute values to make sure that everything stays positive and everything's defined and all that. So that's what's called an LP metric. There's also, you'll note, this is a little different. You might see someday in your life a capital LP. That's a totally different metric, very closely related, but a different metric. So just the little L is the one we're interested in. The big L is just for function spaces. It's a generalization of this to function spaces. So if you ever to find yourself in a class in functional analysis or advanced abstract analysis of some kind, you would look at capital LP metrics as well. So here's a couple of theoretical curiosity metrics just for fun. This is called the discrete metric. Distance between 2 points is 0 if their 2 points are equal and 1 if they're not, and that's it. So is that a metric? Is it a distance function? Sure. Is it a little silly? Yes. It just means that everything's 1 apart, and that's fine. In order to get the triangle inequality, if you went from point X to point Y and then point Y to point Z, well, you would get 2 if all 3 of them are different points. If you go straight from X to Z, well, the distance would be 1. So certainly the triangle inequality holds. If 2 of them were the same, you'd get 1 on the one and 1 on the other. So they're equal in that circumstance, the 2 distances on the left and right of the inequality. And if they were all the same, you would get 0. And then again, the 2 distances are equal. So, and then symmetry is obvious. It's either 1 or it's 0. It doesn't matter which way you go. That's discrete because, as you remember, what the word discrete means is that every pair of points is separated. There's no sort of continuity. You can't get very close to any of them because you always have a distance of 1 or either it's the same point or the distance is 1. And so everything is separated from everything else. And that's why it's a discrete metric. P-adic metric is a fun treat from analytic number theory. So if I have 2 integers, m and n, and we say that and p is a prime number, and we'll define this function that's a Greek letter nu p of m is the largest power of p dividing m. And so, for example, nu p of 30, nu 5 of 30 is 1 because 5 divides 30 exactly once. Nu 5 of 75 is 2 because 5 divides into 75 twice. Then the distance between m and n for a certain prime p is 1 over p to the k, where so k is the smaller of the two of the largest power. So distance between 30 and 75 relative to the prime 5 is 1/5. P-adic metric is really useful for studying advanced number theory under certain circumstances. I spent years of my life thinking about spaces under the P-adic metric, which is why I threw it in here. Also for anybody taking Dr. Zhao's algebraic number theory, you might have come across this. If not, you will come across it if you continue your study in this field. It's just a useful metric for determining levels of divisibility, connects this idea of divisibility of integers with analysis and distance functions, and allows you to bring the tools of calculus and topology into number theory, which opens up whole new avenues of study, whole new avenues of ways to approach problems in number theory. So some practical non-Euclidean geometry examples. You're used to what's called the Euclidean geometry. Probably all of the geometry you studied, probably, maybe not, I don't know, has been what's called Euclidean geometry. We have a flat space and planes are flat and triangles are flat and not curved. Your straight lines are straight and not curved. But spherical geometry is certainly a very practical geometry. So if I have a sphere, say, I don't know, maybe Earth, which is not quite a sphere, but pretty close, then the shortest distance between 2 points is what you get when you traverse what's called a great circle. A great circle is a circle on a sphere that has the same center as the sphere. In other words, it's a circle on the sphere that has the maximum possible circumference. So you could have a little circle up here on the top of the sphere. Well, that is not a great circle because its center is, somewhere up here, a little bit south of the North Pole. Its radius, circumference, diameter, whatever, is a lot smaller than, say, the equator. It's parallel to the equator, but it's much smaller. And so that's not a great circle. The equator certainly is. If I want to measure the distance between 2 points on the surface of the sphere, the way you would want to traverse it is, without leaving the surface of the sphere, is to go along a great circle. If you go along something smaller than that, then you're going to get an incorrect and longer distance. And so, why is that practical? Well, if you're going to fly an airplane from one city to another and you want to minimize the distance because you want to minimize how much fuel you're burning, then you need to fly basically along a great circle. So, for example, I went from direct flight from Washington, D.C. to Beijing, China several years ago, and we flew pretty close to the North Pole. We were over, went well north of Anchorage, Alaska, on the way to Beijing because we're flying along that great circle from DC to Beijing. And so you actually fly much further north than you would expect by looking at a flat map of the Earth, but the Earth isn't flat, so it makes a lot more sense to fly way north. It probably made a difference. You're about 2,000 miles shorter to fly that far north versus taking this, what would look like a straight line on a flat map. And so much, much, much more efficient. Going back to special theory of relativity from Einstein with the fourth dimension being time. So if we have X and Y as events in space-time with coordinates X, Y, Z, and T, then we get this somewhat familiar. So if I look at the piece here, well, that part's really familiar. That's the Pythagorean distance in space. And then I get this weird c squared times t1 minus t2, or t2 minus t1 squared. So you're going to take the distance in time, the difference in time, and multiply that by the speed of light squared, and then subtract off the distance in space. So the time dimension is hugely heavily weighted by the speed of light squared. That's an enormous number. And so this is going to measure distance in space-time in this in special relativity. So special relativity assumes the lack of gravity in order to simplify some things. And so this is the sort of first step in understanding relativity, the theory of relativity. He published this and came up with this in the early 1900s, published it in 1905, failed to win a Nobel Prize for this because it was so controversial that a lot of scientists weren't accepting it yet, but he won the Nobel Prize for his PhD dissertation because he's Albert Einstein, which was a study of the photoelectric effect, how light can create electricity, which is now heavily used in solar panels and all sorts of other things. And then the general theory of relativity came out in 1915 after he spent several years learning enough mathematics to understand what he was trying to do, and came up with the general theory of relativity that does include gravity and generalizes all this different kind of space. So this is an example of a non-Euclidean. This is called hyperbolic geometry, whereas the other is a spherical geometry. Spherical is positively curved, hyperbolic means negatively curved, and flat means zero curve. We actually live in curved space. That's a whole nother ball wax. If you ever want to get me on a good tangent someday, you can ask me about that, but we'll leave that idea right there. So, special relativity is kind of like kindergarten. So we're going to think about special relativity in kindergarten terms, or vice versa, kindergarten ideas in terms of special relativity. So let's say we have a student, Nicholas. So little Nick has 5 red blocks and 4 blue cars. And he's sitting there on the floor in kindergarten playing with his cars and his blocks. And somebody asks him what he has there. And he wants to say he has 9 of something. But what does he have 9 of? Well, he can't say he's got 9 blocks because he doesn't. He can't say he has 9 cars because he doesn't. He has 9, we'll just say 9 toys. So you have to find a category that encompasses both classifications of objects, right? You can't say you have 5 blocks, or you can't say you have 9 blocks or 9 cars, because you don't. You have to find a larger, more encompassing category. And so that comes down to an idea of units. You can only add 2 numbers if they have the same units. This is why we need a common denominator when we add fractions. You really should think of a denominator of a fraction as a units on it. So if I have the fraction 2/3, you really have 2 of something, and those things are thirds. And the thirds are giving you units to work with. And so you can't add 2/3 and 3/4 because thirds are not fourths, just as blocks are not cars. It's the same exact idea. And so you have a different way of finding a common unit. You find twelfths as a common unit, but here you find a common unit by finding a larger category that encompasses both blocks and cars, which in this case would be toys. So same idea. If I go back to special relativity, I can't compare one of the spatial dimensions of a point in space and time to the time coordinate, because the distance function treats those as totally different. So we go back to the special relativity. I can't think of the x, I can't compare the x directly to the t coordinate of a point in space-time, because in our distance function, I'm thinking of the x as very different from the t, because space is very different from time. And so because this distance function treats space very differently from time, as well it should, because space is very different from time, then we can't compare the distance between two x points the same way we compare the distance between two t values, because they're very different. The distance function treats them differently, and the distance function should treat them differently. This is going to come up in a big way when we look at data sets. So here I'm going to take a look at the cover type data set. This is from scikit-learn data sets. There's one called COV type, cover type. So the documentation sends me to this page, the UCI machine learning repository. This and Kaggle are sort of the two leading data set repositories where you can easily find reasonably well curated data sets for use in machine learning problems. And so here I'm going to take a look at the attributes of the cover type data set. You may have looked at this one yourself, you may not have. So it gives you a whole bunch of variables here. And so the first one is elevation. It's going to be the elevation in meters. Then it gives you the aspect in degrees of azimuth, which you may or may not know what that is. It kind of doesn't matter. We can figure that out later or not. The slope of the hill that we're looking at, because we're looking at forest cover and trying to figure out what type of forest cover we're looking at. So the slope of the hill we have in this particular location that we're looking at. We have horizontal distance to hydrology. So how far is it to water? How far is it to water vertically? Then distance to roadways, hill shade at 9 a.m., noon, at 3 p.m., then fire points. We got horizontal distance to fire points measured in meters. And then we've got 44 different columns of data where it's binary. So you have two possibilities, 0 or 1, 0 or 1 for the next 44. So here I pulled up the cover type data set. So you'll notice I'm working on a virtual environment that I called SKL for scikit-learn. I'm running Python 3.7. So I import the function that allows me to fetch the cover type data set. I import NumPy as NP as usual, and then that's going to give me access to the transpose function. So I fetch the data from the cover type data set. I transpose it, and remember I talked about this last lesson about switching the orientation so that the variables become the rows instead of the columns. It's going to allow me to take a look at each of the data variables separately. Just for the first 12, because I know the last 44 are all binary, so I'm going to just skip a lot of those. For the first 12, I'm going to look at, well, variable number, the minimum, and the maximum. So when I look at these, if you remember, some of these are in meters, and so the first one was, I think, altitude. And so it ranged from 1,859 meters above sea level to 3,858 meters above sea level. The second one was degrees of azimuth, and that can range from 0 to 360, which makes sense because they're degrees and we don't need to know anything really all that much more. And so if I look at these, these range, like this one has a range of about 2,000, this has a range of about 360, this has a range of about 66, exactly 66. This one has a range of about 1,400. This has a range of 773. This one's range of over 7,000 possible values. These range 0 to 254. This one's over 7,000. And then I have a whole bunch of variables that range from 0 to 1. Let's say I just have the maximum in a bunch of these, and I'm comparing that to a data point that has something close to the minimum in a bunch of these. So in that case, this variable number 5, whatever it is, I don't even necessarily need to know much about it, is going to have a distance of 7,000 when I just take the subtraction. And if I'm using Pythagorean distance, I'm then going to square that, and that's going to get me something in the neighborhood of 49 million. When I take any one of the last 44 variables, I'm going to get 1, and when I square it, I still have 1. And so this data variable right here is going to be 49 million times as important as this data variable here. Is that something that makes sense? Probably not. I don't necessarily want to weight one variable as being almost 50 million times more important as another variable in this case. And so in this case, if I just throw this into an algorithm, a machine learning algorithm, as is, with my data as is, then a couple of variables that have really wide spreads here are going to have a dominant effect on the outcome. And a lot of the other variables are going to have essentially no impact whatsoever. And so all these variables, pretty much all of the other variables besides variables 5 and 9, where the spread is about 7,000, are going to have a huge outsized impact. These two variables will have a huge outsized impact, and all of the other variables are going to be dwarfed by that. And so, even this first one is less than 1/10 is important because the distance is about 2,000 from min to max. And so that's going to be about 1/25, about 4% of the impact of this one that has a range of 7,000. And this is the next biggest one. And so it's really going to be these two variables, 5 and 9, are absolutely going to take over if I just use a straight up Pythagorean distance function to measure distance on this data set. So here, if I'm looking at the cover type data set, I have got to scale the data values to get reasonable conclusions. And so, I know I encourage you to just play around with it and throw some of these data sets into the algorithms. And so I would expect that you've gotten some pretty poor results out of the cover type data set when you've applied the machine learning algorithms to them. If you got to the cover type data set, what you should now think about doing is going back and really look at, okay, so what do I do with this data set in order to get a reasonable conclusion? And if I do modify the data set or I put it into the machine learning algorithm, can I get better results? And I expect that you should have no problem getting better results when you scale this data set. And we'll take a look at that, or I'll give you a chance to take a look at that. So what I want to talk about here is what to do about it. So we looked at the cover type data set. We know that we have to scale it somehow. And so how do you go about doing that? There's a section of the scikit-learn API called pre-processing. And pre-processing has a whole bunch of different ways of scaling the data sets. The simplest is just preprocessing.scale. This does a linear scale on your data set where it subtracts the mean and divides by the standard deviation. And so that's sort of the most straightforward thing. And then it'll linearly scale all of your data in a range centered around 0 with standard deviation of 1 or a variance of 1 in statistics. It just means that your spread is going to be limited around 0 for the most part. And interestingly, I found that they put this demonstration of k-means clustering on the handwritten digits data, and they include the scale function within this. This is actually part of how I got started with some of this, was when Drew Kessler asked me, why did you use the scale function in your program? And it was because it was in this example. And then when I took it out and looked at it unscaled and found that, in fact, my accuracy went up. And that happened because when you scale the digits data set, you end up overemphasizing some of the pixels that have very little data because they have very little data. And so the variance is very low in that section. And so in order to get your standard deviation or your variance all the way up to 1, you have to spread those points way the heck out. And so you're emphasizing these few rare instances where a pixel has some data in it where it normally doesn't, mostly along the left and right edges of the digits pictures. And so the scale function, the one example they give of using it is actually a place where they've made things worse by using it. And I reran the same program with the scale removed, and it worked better and got higher accuracy, which I thought was very interesting. But scale is very similar to the standard scalar, it's basically the same thing with some different options. So you subtract the average, the mean, and divide by the standard deviation. And the thing here is that this is a linear scalar. And so what that means for us, and the thing to focus on with linear, is you are just translating by subtracting an amount and sliding the whole data set over, and then dividing by the standard deviation. So you're rescaling it, but you're scaling it so that you're preserving proportions. That's what a linear transformation is going to do with your data set. And so one pair of points is 5 times as far apart as a second pair of points. Then after you apply a linear scale, such as the standard scale or such as preprocessing.scale, then there's still going to be 5 times as far apart, the ones that are farther apart. That same proportion is going to happen regardless of whether you've scaled it linearly or not. A linear scale preserves all of those proportions. It only does that within a variable. It doesn't do that across variables. And that's actually the problem within the digits data set, is because the scalar only functions one variable at a time, it functions one pixel at a time, then you end up with pixels where the max is a 2. You're going to stretch that way out so that the max is very large in order to get a variance of 1, a standard deviation of 1. And so your proportions are still there. It's still twice as far from 0 to 2 as it is from 0 to 1, or wherever they get mapped to. But whether that 0 to 2 is the same from a pixel in the left margin to a pixel in the center is definitely not guaranteed, and in fact is not going to happen even close. And so the standard scaler is useful in some of the data sets. If you want to keep that proportionality, you want to use some kind of linear scaler, such as the standard scaler. There are some other simple ones. You can write your own. You just have to subtract something and divide by something else, then divide by something else, or divide by something or multiply by something and add or subtract something, and that's a linear transformation. There are lots of others. You can see them here, and so you can use some of those. Some of them are good. In some cases, you want to shrink the distance for something. So if you have an outlier where a data value is way out in left field compared to everything else, then that is going to have an outsized impact on your calculations in a lot of algorithms. And so you want to minimize the effect of those outliers. Then you'll have to do some kind of nonlinear transformation where those outliers are brought in much closer and you have a non-proportional transformation that pulls those in. So for example, something that's going to shrink distances like that, you have maybe say a logarithmic transformation. So logarithmic transformation, just as an easy example, if you have a base 10 logarithm of numbers, what you're really counting there is how many digits are in the number. And so normally, a million should be 1,000 times bigger than 1,000, right? And so if I take the base 10 logarithm of those, then I get 4 digits. It's really, you get 3 for 1,000, you get 6 for a million. It's always off by 1. It's just 3 more. It's double. It's not 1,000 times bigger. And so you've shrunk that distance non-proportionally and made that point that's way out at a million much closer to 3. It's still bigger. It still preserves the order of things. That things are, things that were smaller before the logarithm are still smaller after the logarithm, but you've changed the proportion of the scale between them so that you can have data that's much closer together and is much more amenable to having these algorithms run on them and having some results that make sense come out of them. And so one of the things you'll have to look at when you look at these data sets is, do I have these kinds of crazy outliers that are going to change things? And I know, one of the students has looked a lot at the California housing, and we found that was a real problem there. And they even have a nice description that here, comparing the effect of different scalars on data with outliers, is a page within the user guide for the scikit-learn. And they try a whole bunch of different scalars on the California database. California database is actually listed as a regression problem. You can make it into a classifier problem by saying which collection of 10,000 or which collection of 50,000, which, break it into ranges and say, okay, we're going to just classify by every 50,000. Is it between, 0 and 50? Is it between 50 and 100? And so on. And then you have sort of 10 classes, and then you're trying to figure out which class it is, and you'll get the price to within $50,000 or within $10,000 and do it as a classification problem. But you're going to need some kind of scalar on it in order to make that data set work, because you've got some massive outliers where you've got areas where the house prices are very strange because you're looking at apartment complexes with many, many, many units. So you got hundreds of bedrooms in a quote unquote house that's included in the house data with a lot of single family houses. And so you need to rescale that data set non-linearly in order to build a data set, a collection that you can work with these algorithms that make some sense, that aren't totally biased by these handful of strange outliers that have very skewed data in them. So I'm going to stop there on part 3 of mathematics for machine learning, and then in part 4 we'll start to talk about calculus, single and multivariable, and why calculus is important in machine learning.